Hey everyone, welcome back. Today's explainer is an absolutely fascinating one. We are taking the whole concept of robotics right out of the theoretical realm of science fiction and bringing it entirely down to earth. We're going to look at how some incredibly foundational rules actually shape the machines that are quite literally changing our daily lives, our workplaces, and, well, our entire future. Okay, let's dive right into this. You've probably heard this quote before. It's the famous first law of robotics, a concept that's been floating around in sci-fi for decades. But here's the thing. It's not just a neat idea for a story anymore. It perfectly sets up the massive contrast we're exploring today. I mean, think about it. How do we take a deeply philosophical rule designed to protect humanity and actually program it into the practical hard reality of steel, circuits, and code? So here's our quick roadmap for today's explainer. We'll start off by defining the modern robot, then look at the laws of robotics, explore home and industry applications, check out medical and defense missions, and finally wrap up with entertainment and agriculture. All right, part one, defining the modern robot. Before we get into the wild stuff, we have to ask ourselves, what actually separates a simple, everyday machine from a true robot? So the crucial point is that a robot isn't just a machine that does work. As you can see, it's a machine capable of carrying out a set of complex actions entirely independently, typically programmed by a computer. Basically, robotics is this ultimate, mind-blowing intersection of science, engineering, and technology. And the entire goal of this field? It's the design, construction, and operation of intelligent machines with one ultimate purpose: to make our lives easier and aid humans in all sorts of diverse ways. But, to actually live up to that definition, a machine has to possess some very specific traits. For something to truly be considered a robot, it absolutely requires these 5 distinct qualities. First step, intelligence, to process its programming. Then, sense perception, so it can actually understand its environment. It needs dexterity to move or manipulate objects, power to actually function, and, this is the big one, independence. It has to execute its complex actions without constant human handholding. These 5 pillars are exactly what allow a robot to actively and effectively interact with the real world. Moving on to part 2, the laws of robotics. Let's transition from those physical, tangible qualities of robots over to the theoretical, hierarchical rules that govern their very existence. And this brilliantly illustrates what we're talking about. These are the 3 fundamental laws of robotics. Number 1, a robot may not injure a human being or, through inaction, allow a human to come to harm. Number 2, a robot must obey orders given to it by humans unless those orders conflict with the first law. And number 3, a robot must protect its own existence as long as that doesn't conflict with the first or second law. It's fascinating, right? Notice how these laws cascade. They strictly prioritize human life way above a robot's obedience, and obedience above a robot's own self-preservation. It's essentially a perfect logical safety net. Now, those laws dictate the pure theory of how a robot behaves, but how do we actually control them in practice? Well, classification of robots based on their mode of control generally falls into 2 distinct buckets: manual or automatic. Manual, as you'd guess, requires a human operator guiding the actions, while automatic relies entirely on the robot's own programmed independence. Understanding this contrast is key because it dictates exactly how these machines are operated out in the real world. Which brings us to part 3, home and industry applications. Let's shift our focus from those big macro concepts to some really specific micro case studies, starting right in our living rooms and factories. A super common example of domestic robotics is, of course, the Roomba. Yes, it's an automatic vacuum cleaner, but it's a true robot because it possesses all those qualities we just talked about. Basic features of almost all Roombas include their independent use of sensors to navigate floors, dodge furniture, and adapt to different surfaces. It operates incredibly efficiently because it's powered by an intelligent algorithm that actually lets it map its environment entirely on its own. Honestly, a real game changer for household chores. Over in the industrial sector, though, things get much heavier. Enter the Cartesian robot. These machines perform highly repetitive, sometimes hazardous, and insanely high-precision tasks. They're heavily utilized for things like 3D printing, but if you look at the automotive industry, they're performing super complex tasks like welding, painting, and assembling parts. They bring just this incredible level of precision, speed, and consistency to the manufacturing floor, dramatically enhancing the quality of the final product. All right, part 4, medical and defense missions. This is where robotics enter incredibly high-stakes environments to preserve and protect human life. Now, what's really interesting about this slide is the Da Vinci surgical system. It is a wildly fascinating example of a manually controlled robot. Basically, it empowers medical teams to perform highly complex surgeries. The human surgeon is in control of a robotic arm while looking through a high-definition 3D view of the surgical site. Because the movements of these robotic instruments are so exact, it paves the way for surgeries requiring incredibly tiny incisions. And the so what here? It directly translates to less blood loss, less scarring, and a much faster recovery time for the patient. Absolutely incredible stuff. Meanwhile, in the realm of defense, we have military drones, or unmanned aerial vehicles. These take on tasks that are simply too risky to send a human into. These aerial UAV robots are equipped with advanced cameras to collect real-time data and surveillance. By sending these machines into hostile environments, whether it's for gathering vital intel or even engaging in combat missions, we directly minimize the physical risk to our human military personnel. Moving right along to our final pairing, Part 5, Entertainment and Agriculture. Here we'll see how robots can mimic life for our amusement, or independently sustain us by growing our food. If you've ever been to a theme park, you've probably seen this next one in action. In the entertainment industry, Disney uses animatronic characters to create some unbelievably lifelike movements and interactions. Think of the It's a Small World ride. These machines are painstakingly programmed to perfectly mimic human gestures, acting as immersive entertainers that completely elevate the experience of amusement park rides and interactive exhibits. It's engineering disguised as pure magic. On a completely different note, the agricultural sector is literally being revolutionized as we speak by autonomous tractors. We're talking about self-driving ground robots that can plow entire fields, plant seeds, and harvest crops, completely without human intervention. They rely on GPS, a network of sensors, and a highly advanced navigation systems to optimize the whole farming process. Not only does this reduce the need for backbreaking heavy human labor, but it actually actively improves overall crop yields. It's feeding the future. Quite literally. So we've seen how machines assist us in factories, hospitals, and out on the farms. But the bleeding edge of this field is what we call bio-inspired robotics. We're talking about machines designed to actively implement the biomechanics, sensory perception, locomotion, and decision-making observed in actual living biological organisms. Which leaves us with this final, rather profound thought for today's explainer. If we successfully build machines that perfectly mimic the intelligence and biology of the natural world, where exactly do we draw the line between a machine and nature itself? Something to chew on.